Okay, guys, so capacitance. So today's date. Okay, so first of all, let me just show you what is it that we're dealing with today. So the capacitance, which is a way to store energy, looks like this. Okay, so next year, or maybe towards the end of this year, you'll be building electronics with me. So this is essentially a battery. So what you're learning with me today is how does it store energy inside? What phenomenon that actually does that? Okay, so there are smaller capacitors is using a different method to make, but if you want a bigger capacitors, you are normally seeing this bigger cylindrical one. Okay, this can kill. All right, if you open a television and you thought that you have unplugged the power, or you are trying to fix a power supply of your computers, what happens is when you, even if you unplug, it's got electricity stored inside. Some of these capacitors can produce more than 1,000 volts. So if you touch it with your finger, you're going to get killed. So therefore, there's a technique which you can discharge the capacitors if you know how to fix things. So that's why you've got to be careful when you touch. Never really fix a power supply unless you know what you're doing. Okay. I just happened at 5 years old, I got home of my dad's screwdriver and I opened up a television while it was still on. Okay. And then I just want to know what's behind it because I thought I keep looking at pictures. So I thought something's behind the television. So I was curious. And there was no one at home. Okay. For Chinese people, they always leave kids in the house by themselves. Okay. So that was pretty close to my seeing my Jesus. Okay. Um, so that's the capacitors. Okay, so let's have a look at what's going on here. Okay, so first of all, let's make sure you guys understand this. So can you now draw? So introduction, direction of current. So this is a symbol for battery. Okay, don't tell me you haven't seen this before, because part of GCSE, which I also taught in physics, they also says that you also use this symbol. So you got positive and negative. The longer line is a positive. And then what happens is you're going to connect it to a capacitor, and that's a capacitor symbol, like that. What is actually flowing in the wire? Thank you. That is the best answer. Most people would say current, but actually there's no such thing as current. It was made up, okay? Because what's actually flowing is actually electrons. The electrons are E minus, and they flow. Why do they flow? Why would they even flow? They are attracted, yeah. They can sense there's a positive side. So the electrons, yeah, remember, unless you're doing special high level physics, that is, we don't talk about the positron, okay, which is the positive electrons, okay. But for now, it's just electrons, because in an atom, outside the atoms, you got 2 electrons in the outer shell, and then you got the next one is 8 electrons in the outer shell. But with metals, there is an electron that's a bit loose, so you can flick it off, and those are called free electrons. So that's why metals has free electrons, which is why it's conductive. So the electron is flowing this side, yeah. So it's going this way. Now, imagine teaching students to do maths with electrons. It doesn't work because it's an object, okay? So what we decided to do is we made up something called a conventional current, because the maths If we do use electrons, they will always come up with a negative value. So 6 amp. So it will be minus 6 amp. So people will be confused. Why is it minus 6? So they decided that current will flow in the opposite direction of electrons. And so that is the conventional I. I is equivalent to current. So that's the first concept. Okay. If you know this, I can admit, so you are actually being taught properly, because most teachers in GCSE do not know that electrons and currents well, they don't know current actually was made up. Okay, so the next thing we're going to do is to look at something called ions. So you got a charge, a particle, a charged particle. So do a subheading, charged particle. So when you rub your clothes, you might create some sort of static, okay? So you got a positive charge, positively charged particle, which I use positive VE. And then you will have a negative charge particle, okay? So this is a negative charge particle. It exists right in front of your face right now. It's everywhere, okay? But there's something you need to know. Okay, this is why there's so nature, our universe is so it's quite stunning, because we only know 22% of particles. We can detect there are the other 78%, but we can't weigh them. We detect they exist, and they're called dark matter. So we're still trying to find out what are they, but we can feel it. Okay, but we can't measure it. Okay, so the positive charge has an electric field going outwards. And they are always perpendicular, okay, to the surface of the charge. So I'm just going to draw a right angle here, okay. So, and then you can make a note here, is always perpendicular, okay. And guess what the negative charge, the electric field does? Inwards, yes. Now, you might not like this, but this is how my physics teacher teach me. We think of positive is the boys or the men, so we give out sperms. Okay, so yes, this is the only way that sometimes it will work. Okay, so if I'm religious as well, but it's just part of nature. Okay, so then the women receives, so therefore that way it guarantees you that you're going to make the right symbol. So they might ask you for 2 marks, draw the field line. Okay, so unfortunately my physics teacher was not religious, so there was a lot of adult content in his teaching. But that's what makes us remember all things, okay? But I won't be using the same methodology, okay? So what would happen when you put the two charges close together? They will attract. Now, this is what would happen when two opposite charges in closed proximity. So we have a plus and a minus close together. Well, first of all, the electric field that go directly horizontally will just find the shortest path to get there. Whereas this one, initially, is going outwards, but then it detects the negative charge, so it bends towards it. Yes, you've done it, but you did it for the sake, probably for the sake of exam. But now we're gonna learn how capacitor work because of this phenomenon. Okay, so again, it will bend more towards it. Okay, etc. So you can think of this. We're not gonna draw it, but it will start to curve. Okay, so and then you will get waves, electric field coming in like that. Okay.
So it starts off
Yes. Yes.
that's how magnets work.
Yes, but we're in magnet is magnetic field, but basically it's right angle to electric field. When there's electric field, there's magnetic field. But we talk about magnetic field when we deal with magnetizations and electromagnetics, which you will see in maybe in a couple of lessons time. So let me just finish drawing this, and then that would do it. Okay. So you might ask to draw a field line like this. Okay. So it projects out. Okay, good. What happens if they are equally charged then? Okay, and then that. So therefore, two equally charged particles in proximity. They would, but what's the field line looks like? Okay, so again, I'm going to stick to a plus and a plus. Okay, so the electric field is going out, so is this one. But what happened is they bend away from each other. And that's the force you feel when you have two magnets of the same charge. Okay. It's the same. So the lines when it goes into the electron. So I think I won't go there. But if you want to, you can have a look at this book. But I want to speed up a little bit more. Okay. Normally I teach this in 2 lessons. I'm doing it in 1. And then obviously the field won't bend to go to the plus side. It just go outwards as normal. Okay. It's only the one that is closest. Now, there's another word for this, the arrows. We call this the flux. If there are more arrows, there's more flux. Okay. So the arrows are called electric flux. Okay. I'll come back to this in a moment. I want to go back to the capacitors now. So now let's look at how charge particles on the parallel plates. Okay, but before that, you're going to pause. I'm going to show you an animations. This is I know this guy because when I was at university research, this American guy was so well known. It's part of his PhD project, and it saved a lot of people's life from learning difficult concepts. Okay, so already, okay, so you can actually download this in your in the App Store, but the better one is this one. Okay. Yes. So this guy's still at Colorado in the US. Basically, he turned all the stuff that we normally can't really visualize by drawing really well, and he does it in here. Okay, so let me see if I can find it quickly. That's it. Okay. So you put a positive charge, okay, is measured in Coulomb, and if you put a negatively charge, and that's what we just done, okay, so it can visualize the field strength for you. You can also measure it by using like a voltmeter. So because the strength is measured in volts, so you can see as I get closer to the charge, it's the strongest, and then when I get away, it weakens. So that's quite obvious. When you go further from the particles, you feel less strength from it. Okay, so nothing surprising there. But when you put that away, and then let's reset this. If you put the two positive one together, and basically that's what we were drawing. Okay, so it's bent. Okay, now obviously you might think what's going on here, but actually it's not fine enough. The arrow's too big, but actually it's going to turn upwards. Okay, or it just maybe stays here with a gap. Yeah. So that proof that with this simulation, that's what it looks like. So hopefully you appreciate now. So if you got more charge, then they will just have lots of arrows like pointing against each other. But when you put a minus in there, then you might alter the arrow. Look, yeah. So you are just basically in the free space, you're distorting the field, right? So when you move, this is what you're doing to the charge. They're quite stable, but when you start swinging around different part of your body, you're bringing electrons or the positively charged particles around this free space. Okay, so that's that one. Okay, so you can also see this as a voltage, I believe. Yeah, you can see that as well. So it's higher, closer to the surrounding, right? So the other simulations, which I will show you, but I'm just going to get it ready. Hello there. Yeah, just put it there. Thank you very much. So give me one sec. So now in a moment, we're going to look at the capacitors, which is this one here. Okay. So I'll just get it ready. Right, let's go back to this. So draw the battery again. Let's get used to it. I would like you always, for the time being, draw an arrow to remind you the current go this way. Okay? Just get used to it. That's why we can use Ohm's law, yeah? We can't really use Ohm's law when we deal with electrons.
So does the current goes positive to negative?
Yes.
And then the electrons go negative to positive?
Yes. Yes, because what actually flowing is an electron. Okay? So, but to do the maths, we need to use current I. Okay? Now, think about what's going on here. The electrons will get to the plate. What will happen? Can they cross? There's an air gap, yeah? So therefore they can't. So what they do is the electron sits here. Yeah? So that's the negatively charged particle. So what would happen is you are going to attract a lot of positively charged particles on that side because they can't cross either. And what happens when you have positive and negative charge in close proximity? You got electric field flowing downwards. You are not wrong, but we won't go there yet. And what do you have here? It's an information of a single bit. Digital. On, off. So basically, when you've got this situation, you got electric field, it's an on, it's a 1. You let go, it's 0. So basically, you are storing a single bit data. So if you have loads of capacitors, let's say 8 of them, you've got an 8-bit binary data. Okay? So, but however, if I build a bigger capacitors, I can store that energy, because this energy is being held. Why is that? Now, don't write anything down. I'm just going to show you something. What do you think would happen when I do this? What do you think will happen to the electron?
They stay there.
If they stay there, they are holding information, even though you cut the wire. That's why I say don't touch your power supply, because the energy stays in the capacitors until I put a light bulb. And guess what? Oh, I can't cross this way. I'll jump across there. And remember, you get energy for your mobile phone. Yeah, you get your energy from your mobile phone. Why would the electricity want to come here? Because it sees ways to merge negative charge with positive charge. And when current flow, you create energy. That's what electricity is about. If electron sits there doing nothing, you get no electricity. So electronics is about ways to get the electron moving. So I got the electron moving because I make them stay here like that. Now they found another route. When they go through here, they do work. And work is electricity turned into light energy. That's why light bulb light up. And then eventually, all these electrons merge together in pairs. Then there will be no more flow, and your light bulb turn on. That's it. That's the concept of electricity. And I really was hoping that I will be the first person to ever tell you this. Well, this is exactly what is happening. This is your Tesla vehicle, your battery inside. You go to the garage, connect this up, yeah, unplug. Now your motor, so it burns. It spins your motor, okay, until all these pairs are all merged together. There's no more reason why they need to join together anymore. So therefore, the bigger your power bank, which means bigger the plate, you got more charge that sits on the 2 plates, then you got longer time to make work done because you got more electrons. Yes, go on first.
The electrons not travel back, I guess, the positive part.
Well, it's actually normally it's the electrons moving to merge with them. Okay, yeah. So because the positive charge actually sitting on the material, they don't move. Okay, because they are basically atoms waiting for a missing electrons. They're dying for. So let me explain. Yeah, yeah. So basically, let me go back to this. Can I just say this is significant? This can take you all the way to your whole. You can study this 9 years because this is how I started to get engaged with electronics. So that's why I picked electronics as my degree. I find this really fascinating. Secondly, is that the atom that you have, which has protons and neutrons inside. So you got 2 electrons in the outer shell, then 8, right? What if let's just say, so 8, so 1, 2, 3, 4, 5, 6, 7. But actually, it meant to have 8. But I deliberately took 1 electron out. So these atoms becomes really hungry to become stabilized because it's looking for an electrons to make it stabilize. And that's what makes it a positively charged. Okay. Whereas an atom, which has an electron stable, but I'm deliberately giving you an extra one. But the atoms is saying, I don't need it, but I will cling on this electron for a while. And this is called a negatively charged particle because there's one electron to freely want to go away. But the positive charge is one desperately want an electron. And the two together wants to collide, want to meet up, you see? Okay? Yeah? Now, but today's lesson, I don't want you to go too far, but I love those conversations. That's what this lesson is all about. So would you agree? If I make the plate bigger, you got more energy stored in the, yeah? You can make more energy. You can make more electricity, yeah? Yes, sir. Yes, plenty. Get in the atomic habit room, there's another small one. Those are faster one. There's one in there. Here, use this one. All the charger in that cupboard. The bottom shelf. Not that one. That one. I put it in. Yep. Yep. Bottom one, and those are all HP ones. No problem. Thank you. Yeah, I'm supposed to be teaching this lesson, but they are teaching themselves. Okay. So so thank you. So happy with that. So in that, if you are happy with that, then now we are ready to look at an actual simulations of this. So nothing happening. I put a battery in. Guess what's looking? So increase the battery, more charge can go onto the plate. Less battery, less charge can go onto the plate. And if you look at this, the more charge goes on it, the bigger my capacitance. Alternatively, I can make the plate bigger to increase my capacitance. I can also make the plate go closer together so that it forces more electron to attract. Okay? And that's how you make capacitors. Those capacitors I show you in the first image on there, which I hope I still got. Yeah. Okay. So then what happened now? I'm going to disconnect this. Watch this. Yeah. So the charge still hold, right? And then you can then now look at this and say, right, let's disconnect. Batteries holding, fully charged, Tesla. Now Tesla going to run the motor. And then look at this. It empties the plate with all the charges. Now you're going to go back to the garage and recharge your battery again, like this. This time, BYD, the Chinese brand, came in and then they get a bigger capacitors. Yeah? So it's got a longer charge, so it's going to light up a little bit longer. Yes, sir. Okay. I know what you're trying to get to, and I'll explain this. So first of all, I won't ask you if you know about light bulb, but in a light bulb, inside here is a lot of wire. It's very thin. But not only that, you might go and find a copper wire very thin. You won't generate light. But it has to be a metal core, tungsten. Okay, very I forgot if it's high resistant or low resistant, but I think it's high resistant, so it heats up. Okay, it heats up and it turns into light because it's so hot. It bright yellow. Okay, that's why it's a light bulb of a yellow color in nature. So when people say, "Oh, can you make me a light bulb that is white?" You can't do that because light naturally made by tungsten is going to be yellow color. I want light bulb in my house. That's because it's not a filament. It uses powder. Yes. Well, have you smashed one? Okay. Lots of white stuff. Well, not white stuff. Okay. But white. There's lots of chemical comes out because it's the chemical and the gas that formulate the color. But one thing to understand is though the reason it lights up is because there's current or electron going through. Okay, you've got to have electron moving. Electron not moving, no energy, no electricity. So basically, you guys, today's lesson is about how to build a bigger capacitors that is smaller inside. Because you might say, well, let's keep increasing this plate area. Well, used to be, 90 years ago when we make a capacitor, it's the size of this room, the plate. Okay, but until someone came up with an idea to make the plate bigger, but not wider. What do you think they did?
Bigger.
Nope.
Are they bigger?
Nope. Now, can I just say this? In the last 7 years, only 2 students has ever come up with this, and that's the Nobel Prize winner. Okay? Nobel Prize winner came up with this idea. Okay? So, I'm going to give you, normally I give you more time, but I want to move on, but I'm going to give you 60 seconds. I'll repeat the question again. Instead of making this plate wider to increase the surface area, to increase the capacitance, what else can you do to save space? Oh, that's good. That wasn't a Nobel Prize winner, but it was eventually another advance. So like a finger, I know what you're saying. So you got plate like this, yeah. But you are still kind of increasing it cross section. That's much more. That's one technique that is much more significant than that. Okay, and that is why I show you the capacitors early on. Okay, so I'm going to bring it up. It's actually a hint. Why is it cylindrical?
Did you like 2 spirals, that kind of?
You're getting there. You both of you are getting there. Someone, strangely, was in Switzerland eating a Swiss roll, and he realized he took a plate and he curls the plate on one side, and then the other plate he curled it into here. And in between, they put a little material that is not conductive to make sure the 2 plates never touches. Okay, so I can actually do a physical experiment next time. I will actually burn a capacitor for you in front of you. It will smoke, and then basically it's paper inside, and basically it's the paper that is separating the 2 sheet metals together. And yeah, very. So that's the art of making these capacitors. Okay, but the car capacitors are different. It's still the idea of making a positive and negative merge together, but they uses chemical. Okay, that's why it's lithium ion. So it used to be when my battery dies, I can add water to my battery, and then it will go again. So you have to keep you use, yeah. So unless you know how to change a chemical, then your battery has to be recycled. 12 volt. Some cars or vans, they might run on a 20-volt battery, but normally it's a 12-volt battery. I'll be surprised to see a 24-volt. It depends on how what's the capacity. It will say amp hour. How many amp, not per hour. In 1 hour, it will give you 60 amp. Okay, so if you are using a hair dryer, they only use 2 amps, then you have 30 hours to use until the battery dies. But the unfortunate thing is, with the old technology battery, your battery can only be 60%. It has to have 60% left. If it go beyond low 60%, your battery will never charge back to 100%. It's the technology involved. But now with the lithium, like your phone is a lithium battery, it can go all the way to 0% and then go up. So when I was your age, my battery was not a lithium, it's a nickel. They say on the menu, when your phone is 60% left, you must charge your phone. If you go beyond it, your phone will not charge back to 60. it will charge back to like 70%, and then next time will be 40% and 30%. Normally batteries, well, the battery, how long you can use it for one charge? Well, though in those days is probably 45 minutes. It was good, by the way, in the context of what I know at that time. But now, obviously, 8 hours, I'm like, what a godsend, you know? PSP, you know those PlayStation PSP one? I bought one. Someone made a duplicate version for 30 quid. And it used to be only 30 minutes of like Street Fighter 2 for it. But now it can do 8 hours. So that's incredible. Okay. So that's the capacitors there. Okay, so now what you've learned today is that you can increase the area of the plate, decrease the separation of the plate to increase the capacitance. So that means if we go back here, so capacitance C is equal to a fraction. Now, that's enough. I used to be a math teacher, so I need to make you understand this. You know, remember the proportional to and the inversely proportional. When you have a letter here, when this goes up, this goes down. That's what it is. Okay, but teachers tend to make people memorize stuff, yeah? So therefore, what did we just say? Something will go drops and then the capacitance go up. The distance drop. So therefore, we can create our own formula. So the D goes here. Distance drop, capacitance increase. This got to be in the denominator. What would increase and would cause capacitance to increase? The surface area A. So the area A goes at the top. Okay. Now, you're probably looking at the formula sheets. Something else would also happen. You can increase the capacitance by putting a material inside. So that is not air. Let's say a piece of wood. Put the wood inside, the capacitance will increase. And that material you see, engineers not like chemistry teachers and biology teachers. We turn every material we see with a permittivity value. It's called relative permittivity. And that is represented by an epsilon. So this is the material that is in between the two plates. Okay, so can I also make you write this? This epsilon is actually equal to epsilon 0 times epsilon r times A over D. Okay, so where epsilon is equal to epsilon naught times epsilon r. Now you just need to use the formula now. You don't, first of all, you know how to rearrange it, know what the meaning is. But today you derive the formula yourself. Okay, that is significant in learning. So now can you take the first formula? You've seen it now. Okay. And right next to it, can you just put epsilon is equal to epsilon naught times epsilon r? Now, looking at the formula sheets, can you tell me what epsilon naught equal to? See if you can find that information. And then once you find that information, take it.
Permittivity of free space.
Yes, you got it. And is it 8.85 times 10 to the power minus 12? There you go. So I memorized it. Okay. So when you go to the exam, you now know where to find things. So give it a take. Oh, yeah. Yeah. So, yep. So epsilon naught here is actually equal to 8.85 times 10 to the power of minus 12 farad meter per meter. Hmm? Yes. Yes. So let me do another diagram here to add to it. So if we so here, this is the capacitors, and you're basically putting a material that is not air. So this is epsilon r. Okay. So a known material. Okay. No, no matter what. Okay, I'll tell you what. Let me give you a summary of different value because it was in GCSE. It is yeah, okay. Examples of materials permittivity. Okay, I even envisage my GCSE, that page number, that book, we had that table in it. Okay, so here we go. There you are. Teflon is like a perspex material, okay? But anyone into 3D printing will know we always use a tube to put our wire in. That tube is called PTFE, has the lowest friction, okay? So therefore the wire will go in without getting stuck. So we use that, okay? 2.1. If it's air, it's 1.006. Okay, many people think it's 1. Vacuum is 1. So if you go into free space outside of Earth, then you get a 1, but otherwise air is 1.06. But I can use those, packaging, they use those white foam, that is close to air as well, okay? Because my students in upper 6 are actually building a capacitors. So they put a plate here and put a plate here, but when they let go, the plate drops. So I asked them, what can you hold the plate in air? They said they were thinking, how do we hold it in air? And then they realize that you can get foam, which is close to air, and they put in between, and then it's got a layer to sort of hold on to it, you see. Say it again. How small? Small on what? Why do you need the material to be small? Okay, I know there's a lot of content. So what do you want the electron to do? To create electricity? What do you want it to do? Yes. All you have to do is create a material that wants an electron, and then put another material that want to give away electron, and then put them close together. If they're far apart, they're not going to know each other needs what they need. Yeah. So they've got to put it close together. So then you generate that. Remember earlier on I put a charge and I put a voltmeter near it. It's got a high voltage. Can be near to generate more output. Now you can generate electrons to move, but if you can generate electrons to run, you will have much greater electricity.
Don't electrons always go at 6 speed?
Mm-hmm.
Don't electrons always go at the speed of light?
No. And that is why it's to do with current. So, well, the speed in which it's going, it depends on how much current you put in. Okay, so, but okay. Now, if we go back to this, so we're not divert too far. Okay, so now there's something else. If you think about it, in the diagram earlier, the more charged particle you see, you got bigger capacitance. So where's the charge particle formula? So alternatively, sorry. You can have a plate with just 5 is less capacitance than this. Remember, to get those on here, you have to connect to a battery. Okay, no matter what, you have to connect to this battery to get this situation. Yeah. So, what formula can I have to include the number of charge? And that's the value called Q. So if you look at the tick that you've done, underneath it, Q is equal to CV. So the capacitance is equal to Q divided by V. Because three variables, I can use a triangular formula, don't I? So Q is equal to C times V. So yeah, so charge. So let's say I put a charge here, right? One charge is 1.6 times 10 to the power of minus 19 coulomb. Okay, it's actually 1.603, but I don't know why I keep remember all this number. But so therefore, if you have two charge, is 2 times. Yeah. So the Q is number of Q. Yeah. So normally we will calculate how many Q there are. So this Q is not just for one particle, it's how many are there in total. Okay. Oh, sorry. So yes. So therefore, when they give you that formula, you need to know how to rearrange it depending what they are asking you. So you got to say, go to the exam and say, oh, this question give me a Q. This question also give me a V, and it's asking me for C. Come on. Unless you don't know how to rearrange the formula, which I'm very worried about this. If you are grade 4 students and you can't rearrange, so if not, practice it before you go into the exam. Okay. So then you substitute Q, divide by V, you got your answers. Done. Easy. Okay. Where does the V come from? The V probably is the battery that's drawn here. Let's say it's 12 volts. Okay. And then it asks you for what this capacitance is if the charge on there, sitting on there, okay, is 6.8 nanocoulomb. Okay, so you got the charge, you got the voltage, so 6.8 divided by 12 will give you the capacitance. Okay, does everyone know what's pico? Okay, well, so let's do this. 1 nanofarad is 1 times 10 to the power minus 9. Yeah. 1 picofarad is 1 times 10 to the power minus 12. Okay. 1 microfarad is 1 times 10 to the power of. No, I deliberately do this. Micro. Nobody knows. 9, I just done nano. It's minus 9. It's minus 6. Micro is minus 6. Yeah. It's about the thickness of your hair. Okay. Now, it's nearly break time. I'm just going to drop a bombshell for you guys. Okay. So remember, C was equal to epsilon R naught epsilon R times A divided by D. Yeah. Now, because you don't do A-level physics, okay, have you ever wondered if we haven't been to another planet, how do we know that the other planet has a gravitational field of a certain value? It's basically what you learned today. Two charges, two planets. Okay? And instead of electric field, they are gravitational pull. No. There is something called the Coulomb's law. Okay, so watch this. Coulomb's law states that um, the formula for the force is equal to G times m1 times m2 over r squared. Watch this. Look at the comparison. M is the mass of your planets. Then the distance from the center to the center is r. Okay? So the greater the distance, the smaller the force. So it makes sense, right? Yeah, further away. Now, here's the interesting one. How the hell do we know that the gravitational force on another planet? Because using our microscope and our we can send pulses back from the other planet, we can actually measure our square. So that engineer can do. Okay, we can do that. Okay. The other thing is this formula. You only need to know your own gravitational field, which is Earth. Okay, and we also know our mass because we are here. We have other ways to measure mass. Okay, and then judging from the and then when we can detect the force, we can actually on planet measure the force that we can sense from another planet. So you will also know this, so we can work out what the mass of the other planet is without actually going over there. Yes. It's strangely that when you go from one point to another point, the energy, the force doesn't drop like this. It doesn't drop straight line. It drops as a exponential curve, and that's where the square comes from. A square gives you an exponential drop. It's called the inverse square rule. Very famous. When you go to university, normally everything is like have a square at the end because everything just drop exponentially. So that's why you got a square. What a great question. Okay, this is. I mean, I am already like back to my university when I lecture undergraduate students. So this is the sort of question people ask. There's a lot of brainy people in the class. But yeah. So I just want to tell you that just because we're dealing with two charged particle, someone, which is Mr. Professor Coulomb, saw those opportunities to see, oh, hang on, if we treat planet as charges, we can also come up with a formula called the famous Coulomb's law. If you haven't heard of it, okay, you need to. This should be one of your most famous law because you are experiencing that force right now on Earth on a daily basis. Okay, the fact that you are not beating Usain Bolt is because you are not overcoming this force. Okay. Anyway, guys, thank you very much.